How's everyone doing today? Good. It's been a long day, I'm sure. This isn't going to take quite 45 minutes, I don't think. I'm glad it's not too large of an audience. Feel free to ask questions, interact with me. I'd much rather this be more of a teaching session than just me lecturing. I don't think that's very much fun for anyone. But we do have to talk about some basics so that we have subject matter to dive into. So again, I'm Bill Westlin. I work here on Jaeger, our distributed tracing platform. Specifically, I work on applied tracing, which are the applications of this data set, interacting with the data set for analytics and insight to power our business. So today we're going to talk about why distributed tracing, how does it work? We're going to go through a little bit of a demo that's available online. We're going to talk about the status of the open source project, a little bit about the architecture, and finally finish with the roadmap and where we're headed. Just as a show of hands, how many people have used Jaeger in the past? Huh? Okay, so why do we need distributed tracing? Well, modern systems are incredibly complex, and they're usually distributed. Amazon kind of started this trend back when they were moving from just a small bookstore into a huge e-commerce website. Nowadays, almost every major website will be built off of many small components that are backed by a set of microservices. So to load any kind of web page, to make any kind of request from a mobile app, there are probably going to be a constellation of services working together to serve you the data that you need. This is a picture of what ours looks like. So these are just connectedness of nodes of services specifically. This is not at an endpoint level. Each one of these services probably serves tens of endpoints. And to show you why this is important, this is what a single request looks like, right? So it jumps around between hosts, between data centers, between availability zones. And we want to know after the fact what just happened, right? Something went wrong. We care about performance. We just want to look for anomalies. We're monitoring a data stream. You can't just look at all of these disparate nodes independently. We need to understand what just happened. And this happens billions and billions of times a day. So this is not a small problem at the collection scale or the analysis scale, right? This is absolutely massive. So we need to be able to tell what is going on just at a very coarse level. We want to see what actually just happened. We need a way to observe this massively distributed system. And we also want to know what went wrong. Did things get slower? We want to be able to analyze performance. Maybe we want to be able to aggregate many of these traces and derive insights into steady state behavior. Maybe we care about capacity or scaling. Maybe we care about comparison between deployments. And this is a, there's a real dollar figure tied to being able to do this analytics, right? 1 hour of downtime for the vast majority of organizations costs about $100,000. For about a third of organizations, this will be above $1 million cost for 1 hour of downtime. And traditional monitoring tools don't really help with this problem. Metrics will show what's wrong, but they have no explanatory power, right? Jaeger, through the context between these disparate events, has explanatory power. It has direct causation, not just correlation. And logs are a mess. There are companies that try to scrape logs and build something similar to tracing, but this is a much more difficult problem. Tracing just drives directly at the solution. So our monitoring tools have to tell stories. Metrics and logs are per instance. Oftentimes they're missing context of what happened before or what the end result was, what the consequences were of the event that happened. It's like trying to debug your code without being able to have a stack trace, right? Something went wrong. I have visibility into the entry point and nothing downstream of that. It's very difficult. So we need to be able to monitor distributed transactions, and this is what distributed tracing gives us. If you think about traces as narratives, we could have some failure in a deployment, let's say, right? And we can notice that and our system will auto heal itself. But we don't know what just happened. All we know is that some event occurred, some rollback took place, right? With tracing, we can see the entire series of events that took place, and we know why. It's almost like a historical memory for what's happening in our ecosystem. Okay, so how do we actually get here? How do we actually get to be able to see traces? How do we collect traces? What is distributed tracing at a high level? So you have some service A, which sits at the edge of your ecosystem. And a request will come in. When this happens, we start what's called a span. A span represents logical work that takes place at one service. So we have a request coming into service A, we're starting span A, and you can see that it proceeds from left to right across time. Well, service A calls into service B also. So this is visualized in a trace view, almost like a Gantt chart, if you're familiar with Gantt charts. So we can see here that for part of the duration of A, it had called into B and is awaiting a response. We can see that B calls into C and calls into D. We can see that it calls into C before D, right? This takes place previously in time. But both of these are nested underneath the call to B. So we can explain the duration at B by being due to the downstream requests into C and D. Does this make sense? Yeah, okay. And then after returning from the call from B, we call into E. Now, it doesn't necessarily indicate that this call to E is dependent on the call to B happening. This could just be the way that the code is written. So maybe we have room for an optimization here. If we want to reduce the time at A, maybe we can call into B and E in parallel. This is the kind of power that tracing gives you. It allows you to see the entire picture, make hypotheses, and test them. So I mentioned this before, traces are narratives. These are a story of what's happening in our business all the time. If we care about solving any problem within our business, for the most part, we can do it by watching tracing. This allows us to both look at aggregate behavior, steady state behavior, and isolate very specific individual transactions and see the complete transaction that happened as part of that. We can also see causality within a transaction. We can see that a failure at a previous request caused another downstream to not be called, or to call and also experience a failure because it didn't have the right data to pass. Okay, so explain tracing at a high level, what a trace looks like, what these spans are. So let's actually go test this out. So we have a hot rod demo available online. Let me switch my screen here. Cool. Okay. So there's a Medium blog post called Take Open Tracing for a Hot Rod Ride. This is fantastic. It was written by Yuri, who is the tech lead for the Jaeger project. Very, very easy. Everything that I've done here, I set up in about 10 minutes before I walked down to this room. You just install the Docker container, spin up the application, and you can play around with Jaeger. It takes 5 minutes and you can mess around with it. So this is what you get when you spin up that app. It's called Hot Rod, Rides on Demand. Hopefully that sounds familiar. So you can order flowers, chocolate, dessert, or coffee through this application. So let's try that out. Okay, so we clicked on the amazing coffee roasters. We can see dispatching a car, arriving in 2 minutes. We see that we get request IDs, we get some kind of like driver license plate, and we have the latency of the request, right? Japanese desserts, chocolate. Okay, so now we've made a few requests, but we want to know what actually happened with these. Did they succeed completely? Were there retries? How many services had to coordinate to serve these requests? This is what Jaeger shows us. So if we look, these are the set of services that we can search within. Because this is a very simple demo, this search functionality isn't all that useful, but normally you wouldn't have every service involved in every trace. So here we're going to get the same set of traces regardless of what we search for. Let's go ahead and search for front end. Okay, so we can see we had a 716 milliseconds, 776. These are all from a few seconds ago, a minute ago. Let's take a look at a single request. Okay, so new to open source, great work by one of our interns are these collapse and expand buttons. This trace, this might look complicated. This is a very, very, very simple trace. Within Uber, these traces typically have many, many thousands of spans. So collapse all, expand all, very much your friends, and these are relatively new. Okay, so we have this request into the front end service for get a dispatch. By expanding one depth level, we can see that we are calling into the customer endpoint, driver find nearest, and the route finding endpoint multiple times, okay? Just with this amount of data, we could analyze the performance. We could try and improve the performance of the service. Does anything stick out at people? Something we could do here if we wanted to shorten the duration of this request? What to improve latency? Shout it out. Parallelize the operations, that's great. So it looks like they're a little bit in parallel. I'm kind of just like visually matching this with my eyes, but it looks to me like we've got a worker pool of 3 making downstream requests, because it looks like these 2 get kicked off once these 2 stop, and then this guy here gets kicked off once this one's finished. So it seems like we start with an initial set of 3 requests. Each time one finishes, we make a different downstream. So we could increase that worker pool size, right? We could probably get some more parallelism. But that's going to get us at most the maximum length of any one of these downstreams, right? Even if we did them all in parallel, it's still going to be limited by the maximum downstream. And these seem to be much more pertinent for an optimization, right? They take a lot longer. So we can't tell why they're taking so long yet. So let's dig into one of these. This front end customer endpoint, we can see, let me step back for a second. So this might be a little bit confusing. There are client spans and server spans. Client spans are a service intending to make a request, attempting to make that request, and the server span is the opposite service having received that request. So these come in pairs. You can see that we have a front end get/customer, and finally here we have an actual customer service with that endpoint. That's because this is front end here saying, I intend to make this request downstream. The delta between the start and end times could be inferred as network latency. This isn't always the case, right? You could start a span, put something into a worker pool, have it dequeued sometime later. But it does show the difference between the real intention to start the request and when it was received. That can be explained in a lot of different ways depending on where your domain is. Anyways, if we're trying to optimize this initial portion of the request, we can see that it's entirely dependent on MySQL. So we're gonna have to do something with MySQL, and MySQL doesn't just naturally scale, so we can't just throw some instances on this. This doesn't seem like a good fit for an optimization. So let's look at the driver endpoint. Okay, here we have a good chance, right? So all of these Redis calls are made in series. They're all called get driver. We can actually look at some of the details. So we can see that the driver ID here is like 6274C. Here we have a different driver ID, right? Again, a different driver ID. So we're actually just scanning for drivers in the area. This isn't dependent on any previous driver calls, right? We could do all of this in parallel, very trivially. And if we were to do that, let's take a look at what we can estimate our performance improvement would be. Well, the longest Redis call I see here is like 40 milliseconds. Let's say theoretically it could be double. Well, we could still do all these in parallel, get down to 80 milliseconds, which is like what 160, 180 more than where we're at now. So that's a pretty decent improvement for just changing something simple like if this is a Go service, maybe you just put the Go keyword in front of all these downstream calls, right? Get them all in parallel for free. Any questions about how you go about using Jaeger for analysis? I'll also point out that we have pretty detailed logs and tags attached to all of these spans. So at the very top level, through the logs, we can see the entire series of events that took place without needing to look at the traces. And then looking at every single downstream span is going to give us different details because it's scoped to that service's perspective, right? So at the top level, we get events like looking for drivers, founding drivers, trying to find the route, found routes, dispatch successful. If we wanted to dig into any one of these individual requests, we can see that here when we're hitting the customer, we're just hitting a database, loading customer, that event takes place. Right? This wasn't part of the top level logging because it's scoped to the responsibilities of the service that are emitting these logs. So this is a really powerful thing. You can attach any kind of tags or logs that you want here. We can scrape these tags and logs out of traces. We can filter traces down, aggregate around tags, cohort on tags, and analyze within individual cohorts. This is the kind of work that I'm mostly doing at Uber. I don't do very much of the core platform work. I do mostly aggregated analytics and insights. Okay, anything that anyone would like to talk about here before we move on? Cool. I'll also point out, since this is an open source presentation, so we actually got a great contribution last night that takes this graph and instead of making a Gantt chart view, makes it more of a directed tree, a directed graph. So we love all of you in open source. Please contribute. If you have ideas of how we could do better, we'd love to hear that. So please brainstorm with us. And come up after if you'd like to hear anything more about how we could work together, or if you want to hear anything more about Uber use cases that I'm not really going to talk about in a public presentation. Okay. Okay, so through this one system of distributed context propagation, we're getting a lot of different value. We're getting the ability to just monitor distributed transactions. You can set up simple filters for alert me whenever the volume of requests that hit this downstream exceeds some threshold. Just in a general sense, we're commoditizing and democratizing access to this data. But we also allow for root cause analysis. So on those spans, as part of the tags and logs, we also surface errors. So when you have a failed request, you can see exactly why that's happening. If that service is emitting really good error messages, it should be exceedingly obvious. If there are huge latency delays, that should stick out like a sore thumb, right? Whichever span is taking the longest, this is probably the cause of your timeout. So it's really easy to do root cause analysis with Jaeger. This is one of the use cases that we've really doubled down on internal to Uber. Performance and latency optimization. So we walked through in just like a minute how you could optimize a very trivial transaction. Think about doing this at huge scale, right? By analyzing every transaction that comes through your system, you can spot inefficiencies. Maybe this service only takes, double latency when service X calls into it. Maybe it only takes that long when service X calls into it with a certain intrinsic data size. The payload itself is taking a while to compute. Right? These are the kinds of insights that we can derive through tracing. Service dependency analysis. At smaller companies, maybe this isn't as vital. At Uber, with the many thousands of microservices that we have, this is actually really critical just for developers to be able to do their every day-to-day job, right? If you're calling into service X and that doesn't succeed, and you talk to the owners of service X and they think it's a dependency that's failing, you're pretty much stuck without Jaeger. You don't get any insight past that initial wall. So Jaeger allows you to see through boundaries by connecting context. So Jaeger's open source, that's why we're here. We're part of the Cloud Native Computing Foundation, CNCF. So you can see us up here along with all of these fantastic projects like gRPC and the umbrella of Jaeger, Open Tracing. So this was started at Uber in August of 2015. We've been using it extensively since then. So this is hardened through our scale, built and tested for Uber. We open sourced this in April of last year. We joined CNCF as an incubator in September of last year. And we're currently undergoing the graduation process. So this is really a milestone that signifies continued customer support, reliability, and durability. And we have built-in open tracing support. All of the Jaeger APIs go through a layer of open tracing API. So yeah, a little bit of humble bragging. We're decently popular on GitHub. And we're used pretty actively throughout the community. So these are actually just companies that have given us statements. We know that many other large tech companies are also using Jaeger because we get questions from them occasionally. And contributors are welcome. So I would love to talk to all of you here, any and all of your ideas, and help enable you to build those. Like I said, we got a great contribution last night in open source. We'd love to collaborate as much as possible. Okay, let's talk a little bit about how this actually works, how Jaeger collection works, and some of the advances we've made in our architecture over the last year. So we have We have backend components in both Go and Java. We have pluggable storage, so you can run off of an in-memory adapter, Elasticsearch, Cassandra. The UI is written in React and JavaScript, and we support all of the open tracing instrumentation libraries. This was the architecture last year. Boxes and arrows, I apologize for that, but these diagrams kind of fall into every presentation. So for every single host, we have some application running, which instruments its client libraries with Open Tracing API and Jaeger more specifically. This Jaeger client is emitting spans to a local agent on its host, right? So you can have many, many applications running on the same host, and we have a centralized collection and also downsampling tier at the host level. So trace reporting, thrift over UDP. We have a bit of control flow back into the Jaeger client. This has to do with sampling probabilities. This gets pushed into the collector. Again, there's another feedback loop for adaptive sampling into the agent. The collector then forwards them into Cassandra, writes them to Cassandra, and then they're queried out through a Go service. This is the Jaeger that you're probably all most familiar with. And this is our architecture today. So now the agent is speaking directly to the collector, which is dumping these spans directly into a Kafka queue. From there, they're asynchronously ingested. So the problem here is that these memory adapters can get backed up, or sorry, these memory queues can get backed up. So if we have very spiky data, we can get a really large queuing effect here, which means that we have delayed writes into Cassandra. It also means that we're getting back pressure onto Cassandra. I don't know how many of you have used Cassandra before, but it works fairly well until it doesn't really work that well at all. So trying to push this much write load along with heavy query load on Cassandra is troublesome. Now what we can do is asynchronously ingest into Cassandra. So these are all in a streaming job, which can back up or be DQ'd at whatever rate we want. So we can maintain a constant stream of ingestion instead of this spiky workload. So we also have a lot of new Jaeger features. So we talked about adaptive sampling here. Adaptive sampling is really important because service owners don't really understand the impact of their sampling decisions. If you sample a top-level endpoint, you're going to need to do it at really low rates because this is the gateway into your ecosystem. But you don't know what that's going to do to all of your downstream sampling decisions. You don't know if your service grossly sampled at like 50% is going to have some endpoints with huge QPS and some endpoints that barely get any traffic at all. So what we're doing is monitoring throughput on each service endpoint pair. And we're adaptively changing those sampling decisions through basically a PID loop. Okay, so if your service's traffic goes up, your adaptive sampling decision will go down. And overall, we try to maintain a constant stream of traces collected through any particular endpoint. Asynchronous ingestion. So I already went through this a little bit, but synchronous ingestion was unable to cope with the traffic spikes we were receiving. We just allow any service to start tracing at Uber, right? And we're going to do our best to attempt to collect that. Before we had adaptive sampling that was really well built out, we had these huge traffic spikes because a new service would come online. They didn't know all that much about how to do sampling decisions correctly, and we'd get a huge percentage of like 100% sampled traffic. So this is going to cause a really bursty load until we have the ability to go reach out with these service owners. So asynchronous ingestion combined with adaptive sampling really solved our bursty load problems. This is a feature I'm really excited about. So we now have structural and durational comparisons of traces. The duration comparison is coming, I think, in the next couple of weeks. We've been extensively using this internally already. So you can imagine looking at two requests, one of which, let's say, takes twice as long as the other. Well, one way to do this comparison would be open two browser windows, load the trace in one and the other, go through each span, attempt to compare the duration, see what took the longest. That works at a human scale or for a small trace. But again, the traces we're talking about here at Uber are many, many thousands of spans. So we really need a way to understand immediately what the difference between these traces are. So what we're looking at here is a structural comparison. So trace A here is being compared to trace B. We can see these are both winter mute, deliberate icebreaker. These are made up endpoint service names. So trace B here is missing all of these subtrees that are indicated in red. And trace B also has additional calls that are highlighted in green. So you can see what took place in B that didn't happen in A, and also what didn't take place in B that happened in A, right? And you can very easily select many different traces, swap between them, swap the A-B comparison, so you're comparing B to A and vice versa. This is also very, very useful for duration comparison. When you have the same structure of the tree, but one of the paths took longer than another, right? Before you knew that one trace took twice as long as another, you could search the traces and kind of suss that out, but now we just have that path glowing red, right? It's exceedingly obvious. This is the entire dependent path that returned this additional latency, right? So your eyes just jump right to it and you don't have to do that much analysis. Kubernetes operator. So this is just to make it much easier operationally. You can just stand up Jaeger on Kubernetes. This is meant for small shops to just be able to deploy Jaeger pretty trivially. So what's coming next? Incomplete span support. So this is pretty exciting. We're trying to do a lot around the notion of streaming traces, asynchronous processes, external API calls where you might not always have access to instrument certain pieces. We still want you to be able to have tracing. So part of this story here is incomplete span support. So you can imagine a long-running job, which is continuously pulling from a stream, executing some work, and then pushing it into another stream. That job is going to have a span that lasts theoretically forever. So we want a way to cap off a workflow and maintain that context for a long period of time. So this is the ability to basically finish spans before they're really finished. This is like a pseudo finished. So with incomplete span support, we can get full traces even when that process is still ongoing. It's kind of like a checkpointing finish. This is particularly bad when the root of the service is the long-running process. That's mostly why we need this. And you can imagine at Uber, we have certain processes where people are online for hours at a time, right? We still want to be able to see requests from those main processes. We want to be able to link them together as being from some shared source. Protobuf and gRPC. So this is really exciting. The internal model has been on Protobuf, but the collector and the query, I believe, use T-channel, which is Thrift. So we now have external APIs, or coming soon, external APIs that are running on top of Protobuf and gRPC. This is exciting because standardizing on gRPC allows for better routing to collectors. You can load balance across collectors with third-party off-the-shelf solutions. You're going to get transport security for free with gRPC. This is just kind of centralizing onto technologies that have become more popular since Jaeger started. And gRPC also allows for pluggable storage. Go plugins are fairly immature. However, there are these kind of separate services that communicate over gRPC that you can plug various storage backends into. So by moving to gRPC and Protobuf, we enable you to use third-party pluggable systems because the Go plugin ecosystem just isn't there yet. Data analysis platform. I'm really excited about this because this is the space where I work for the most part. And I've been doing data analysis in sort of an ad hoc style, spinning up services for aggregation where I need to, building streaming jobs, stuff like that. This is going to be a complete story for you to test out a hypothesis, back test it on historical data, and then once your hypothesis has been proven, trivially spin off your job into something productionized, something that'll run on a Yarn cluster. Right? So you can just very quickly, locally, maybe in a Jupyter notebook, test out some algorithms on some data. You're seeing good signal, it should be trivial for you to spin that off into something that's long running. That shouldn't take a lot of effort for you as a developer. Integrations. So we talked about logs in the context of a trace. We just want to keep running with this. So stack traces, exceptions. You should be able to click on a node and jump to source graph and see any of the source code that was run as part of that span. Maybe you want to see what subsystem this span is part of, ownership in some way. Maybe you want to see an on-call engineer because you're seeing an error as part of that, and you're responding to some kind of ongoing incident. Deep linking into a subsection of a trace. When you share a trace with somebody right now, oftentimes you have to kind of explain where they need to scroll down to and expand this tag, and then you're going to see the data that you want. We really want you to be able to link share, and it's exceedingly obvious what you're trying to show that person. You don't need to be sitting next to them. You can send them a link. It's going to have a span expanded, text highlighted, an error message. Just very, very obvious that this is what you were pointing to when you sent them that link. Cool. So I just want to open up the floor to Q&A. I would like to talk a little bit about what we're using tracing for at Uber in an abstract sense. So I mentioned this before, but we're doing lots of aggregations of tracing, and we're hoping to figure out a way to move this into open source with the data analysis platform so that it's commoditized for all of you also. So these are things like looking for efficiency improvements, figuring out how latency of one service affects another. So let's say you want to make a reduction at a top level. Looking at a single trace allows you to make a hypothesis, right? When we ran through that hot rod demo, we didn't know anything about how representative that single trace was. Maybe that was one bad performance example, and usually these things are run in parallel, right? So we want to be able to go from one trace to a larger sample set that's representative of what we were looking at, perform analytics on that larger sample set, right? Or tell us whether that single instance is representative. Jaeger is basically a context engine for events. You can think of it like that. So Jaeger is very useful for bridging organizational divides. You might not have insight into the services or the metrics that other teams, other organizations have. But if you pass context along, you're still able to get that trace back. So we can bridge infrastructure divides, we can bridge organizational divides, we can even bridge cloud and on-prem. Right? So this is something that's very useful for tracing. We're using this for root cause analysis and detection. This is something that we're really hoping to be able to speak about publicly next year and bring into the open source, right? So if your workloads for your business are failing, tracing should be telling you why. They should be telling you why with explanatory power for your customer. And so that's another direction that we're heading in. I think that's pretty much it. Does anyone have any questions? I'd love to have more of an open discussion if possible. Yeah, go ahead.
Let's say, I actually don't know if it's true. I'm assuming that in order to actually build the entire for you getting an Uber type of driver destination, the traces, wait, I guess you traces and like convenient.
Yeah, so this is more what we're talking about with the data analysis platform. So you could imagine describing a predicate. You just talked about a tag for a driver UUID or something, right? Okay, well, you want to aggregate within that predicate. Maybe these are only traces that go to a certain data center. Maybe these are only traces that are running a certain version of code, right? Aggregate within that data set, aggregate within another cohort and do comparison between them, derive insight from one of them, explain structural differences, latency differences. We really want to expand this to be generic analysis. Select one thing, select another thing, tell me something about both of them, tell me about their difference and similarities. That answer your question? Okay. Yeah, so we have a lot of internal tooling around tracing that we can't quite share publicly yet. So this is what we're talking about publicly as the data analytics platform. So yes, we'd love to have available summaries, let's say, of these tags. What's the breakdown of tags on a certain endpoint or a certain service? We'd like these tools to be immediately useful for pinpoint use cases and then kind of generally expandable to answer any kind of question. We are really first and foremost focused on use cases for our business, and then kind of generalizing them for open source. So I think, obvious problems that are easily solved through tracing are any of these kind of latency explanations. I think, Amazon with Dynamo kind of popularized like the P95, the P99, the P50, right? But I think a lot of research groups are realizing that variance between services is very important, especially in a tightly coupled SOA like we have here at Uber with many thousands of services. What matters more than just kind of average behavior is the variance within that behavior. Okay, so we'd love to show you tools that analyze variance as it moves throughout a stack. It might not be the case that the P99 latency service is actually having as much of effect as you think it is. Maybe it's the one with the most variance in its latency, because that gets magnified as you move up the stack. Right, so we want to build tools like this where you can just kind of trivially select a portion of a trace and say, show me everything that has this pattern in it, right? And then aggregate stats within that. So we've really been trying to prove this out so that we know that this works well. It works for a lot of use cases internal to the business, and this is coming to open source soon.